Perfect. We'll get started. So I wanted to use innovative teaching practices because that's what the university wants me to do. So the innovative teaching practices, I want to show you some real world examples of dynamical systems that has unstable behavior, and that will help you understand and appreciate some of the theory that we are going to study in the coming few lectures. So this is about a trailer that flipped. I don't want YouTube Premium. Okay. So this is about a trailer that flipped and it ended up flipping the car. So if you are scared of watching accidents on YouTube, you can maybe close your eyes. But I will just show you the unstable behavior. So you will see a trailer here, a car with a trailer, a truck with a trailer, and after a bump, so that's an impulse response. The trailer became unstable, and then it whatever led to the accident of the specific vehicle. Okay, this is a famous bridge collapse. If I'm not mistaken, this was in the Washington state, but I could be wrong. It was in 1940. So the bridge was $6 million cost bridge. It was opened in 1940. Within 3 months, this is a sustained wind of 35 miles per hour going over the bridge that leads to oscillations within the bridge, and in a few days it collapsed due to those oscillations. And so 35 miles an hour is not really a huge wind. I mean, it is strong, but it's not very strong. But what happened was that the bridge extracted energy out of that moving air, movement of air over the bridge, and as a result of which the bridge collapsed in a few days. So you see this bridge collapsing and falling down in the river. So it happened there. Now, this is the simulation of what happened on Tacoma Narrow Bridge. It's actually a very good case study in a lot of civil engineering classes and fluid mechanics classes, but I'm using it as a case study in a linear systems class now. Okay, so you have a dynamical system with some air moving over the dynamic. I mean, it's not quite a dynamical system, it's supposed to be a static system. But when air is moving over the system, it ends up becoming a dynamical system, as a result of which what happens is whenever the air flows over it, and if the bridge is in a specific direction, then the flow of air creates the lift on the bridge, as a result of which the oscillation starts building up, and that leads to the eventual collapse of the bridge. Okay, now this is more of a modern example. So you have a whole bunch of tall buildings all over the world, and because of the airflow over the buildings actually shake. Have any of you gone to some of these older churches in Europe, tall churches in Europe? No. So if you stand at the tall churches in Europe, you will actually move like this at the top of the church. Okay, so it's just the way churches were built. I mean, they are all stable, they've been around for 400 500 years, but as air moves over the church, over the building, it actually moves. So these are all the tall buildings in the world, and as wind flows over those tall buildings, it leads to oscillations. And in order to control those oscillations, what they generally have, yeah, so you're seeing all these different simulations of oscillations over tall buildings. And I want to skip to some of these simulations. So they put something like a mass and a damper system at the top of the building, and that reduces the oscillations within the building. Okay, and so this is the real big mass in a building, probably in Taipei, and these are the dampers, and it reduces the vibrations within the building, especially if you are at a very top levels of the building. Okay, so what's happening in all these processes? So you have essentially, you wanted to create a static system, but what happened was, because of the airflow, because of whole bunch of tornadoes. I mean, you could have a regular airflow, and you could also have natural disasters like earthquake or tornadoes. And you want these buildings, these static structures, to remain stable and not collapse even under those circumstances. And so, of course, there is a lot of work that has been done. So every time a failure happens, and people try and understand why those failures happened. And so initially they thought it's a static thing, so we don't need to have a dynamical model of the system. But then they realize that, okay, they now need a dynamical model of a system, and assuming it's a linear system, which around the equilibrium, it's all going to be behave linearly until something really bad happens. So going back to this particular example, in this case, it's within the linear regime. It's a linear system, but it's close. When it's close to collapsing, it no longer remains a linear system. It becomes a non-linear system at that point of time. So as long as you are close to the equilibrium state, you will remain linear. And now, today onwards, we are going to try and understand how exactly is that system going to behave. Is that system going to be unstable? Is that system going to be stable? So stability is a huge deal. So we'll talk about stability in some time. But before we talk about stability, we'll talk about eigenvalues, eigenvectors, eigendecomposition, and things of that nature, which I'm sure some of you might have seen in your linear algebra class. But the goal here is to collect all of those results and then take it to the next level to try and understand what happens in the linear systems case. Wonderful. So as we had talked about, I want to have a simple system initially, so I don't want to talk about time varying system. If instead it was x of t naught, then the solution is it's given by this expression. So we want to essentially understand this matrix exponential, what exactly it means to take the, like, what are the expressions for matrix exponential. So that's going to be the topic of discussion for quite a few classes. I want to give you a few examples. So we saw the structural vibrations. Videos, you could have satellite orbit, acoustic, aeroacoustic flutter. So these were the examples that we saw in the videos a few minutes back. These models are given by x dot of t equals to 0 identity. I'm already using A. Let me use B1, B2, xt. So the A matrix looks something like this in these sort of applications. And then there is Leontief model for supply chain. And here the dynamics is given by x dot t equals to B1 inverse I minus B2 xt. And then if you have a demand, then you add this to the expression. And if you have a mass spring system, you have this is the typical mass spring dynamic system, and K is the spring coefficient, M is the mass of the object, and so this is what the A matrix looks like. And then you can add a damper to this particular mass spring system, then it becomes the suspension in your vehicle, and that has some additional terms in the matrix. And so for high-end vehicles, so if you were to go to General Motors or Ford Motor Company or Audi and so on, or even companies like Toyota and Honda, and if you work on their highest end cars, so the cars that cost $100,000 in the market, you have to worry about their suspension system. Okay, and so there again you are going to be studying a linear system, a linearized model of their suspension system, and figure out what sort of control strategies would lead to lower vibrations on the road. Lower vibrations on the road means you will hear less road noise inside the cabin, and that gives the person a very good driving feel, and therefore they are willing to pay $100,000 to buy the car. So these are all the examples of systems of this particular type. Okay, a few things that you must have noticed. Sometimes whenever there is a impulse in these systems, the state of the system converges to zero exponentially fast. Sometimes you see vibrations that are damped. Sometimes you see vibrations that are constant. So for instance, in the case of satellite, it's not quite a vibration, but it has a cyclic orbit. And so the satellite is moving in that cyclic orbit forever. I mean, not forever, but for 50 or 100 or so years. Uh, Earth has been moving around the sun for millions, maybe no, not millions, billions of years. Okay, so those are the kind of situations where you have undamped systems, and then you could have systems which blows up, and then it leads to some sort of accident. So either a building collapses or a bridge collapses or some sort of bad behavior happens. You have aeroacoustic flutter also. I mean, air related flutter also in aircraft wings. So if you have taken a flight and if there is a gust of wind coming on the aircraft, you will see that the wings are moving up and down inside the airplane. It doesn't really affect you inside the airplane, but you will see the wings moving up and down. So I find it very dangerous, but whatever. I'm just fearful of flying. Okay. So the question is, we know that if we have the model of the system, so somebody spent hundreds of hours deriving the model for structural vibrations or satellite dynamics or aeroacoustic flutter. This model is used in supply chain to figure out capacity, to figure out how much, uh, what are the risks to their supply chain model. So it's an economic model. It's not really something we study in engineering. So if you were to take a business class or an economics class, you will probably study this model. And mass spring damper kind of system, you definitely have taken some physics class where you've studied these. So somebody spent hundreds of hours trying to figure out this A matrix, and now our goal as linear systems people goal is to figure out what the behavior of that system going to look like. And what that means is, I mean, some mathematician back in 1700s told us that, look, if this is the system, this is what the solution is going to look like. So essentially our goal is to understand how to compute this exponential of AT and then figure out what's the behavior of the system going to look like. Any questions so far? I want to remind you that exponential of a matrix A is summation a raised to I over I factorial. I goes from 0 to infinity. So this is the same as I plus a square over 2 factorial plus a cube over 3 factorial and so on. Okay. Let's do I'm trying to come up with some examples. So let's do exponential of lambda 1 0 0 lambda 2 t. What do we get? We get 1 0 0 1 plus lambda 1 t 0 0 lambda 2 t plus lambda 1. What's a square? I think it is lambda 1 square t square 0 1 over 2 factorial. Do you see a pattern here? What do I get if I do this sum? What kind of pattern do you see here? So I have 1 plus lambda 1 t plus lambda 1 square t square over 2 factorial plus lambda 1 cube t cube over 3 factorial and so on and so forth. So that's exponential of lambda 1 t. I have 0, 0, 0, 0 everywhere. So I get 0 here, and I get exponential of lambda 2t. So if I have a diagonal matrix, so if A were a diagonal matrix here, my solution to the system is going to look something like this. So things are easy. When things are diagonal, things are easy, right? Any questions so far? Perfect. I want to talk about an important result. Let me write it here. Lemma. Suppose A1, not A1. Let me do A and B. A, B are two n cross n matrices. If AB equals to BA, then exponential A plus B equals to exponential A exponential B. So if I have two matrices, then this identity holds. Does it hold for scalar values? If a and b were scalar, would it hold? So we know that this one holds. Exponential of a plus b equals to exponential of a times exponential of b if a and b were scalar, right? Because scalars automatically satisfy this condition. Scalar multiplications commute. This is known as the commutativity property. So matrix multiplication does not commute. So AB is generally not equal to BA, but in some cases AB equals to BA, in which case this is going to hold. Let's see why that should be the case. Is it obvious why this should be the case?
Scalars or for matrices?
This is no, not for scalar, it is obvious, but for matrices, why should this be the case? Let's think about it. Let's look at it in a bit. Uh, if A is identity matrix, this is automatically satisfied, right? So if A was identity, so exponential of I plus B is always exponential of I, exponential of B. Okay. So let's see. Exponential of A plus B equals to identity plus A plus B plus A square plus AB plus BA plus B square over 2 factorial. Now what is exponential of A times exponential of B? Okay, so I have this expression here and I have this expression here. I want you to stare at these two equations for a long time and tell me if I can cancel these two terms out. So I think I see an identity here and an identity here. I see A plus B here, I see A plus B here. So I can cancel those two terms. But I have this term here and I have some other random terms here. So How do we cancel things out? Can we do that? So I have a square over 2 factorial here. I have a square over 2 factorial. I have b square over 2 factorial. Where is b square over 2 factorial?
The second a square should be b squared.
Oh, I see. Okay.
Or,
Yes.
yeah, either that first one or the one.
That's right. That's right.
That A is correct.
That a is correct.
That A is
Okay.
correct. But the second A square over 2 factorial is.
Oh,
We should
this
make
should
b
this should be b square. Yeah. Perfect. Thank you. Awesome. Okay. So this a square cancels. Let me cancel them. This identity cancels. This a cancels. This b cancels. This a square over 2 factorial cancels with this. B square over 2 factorial cancels with this. But I have an AB here. But I have AB plus BA over 2 factorial here. But guess what? AB is equal to BA. Right? So this term cancels with this particular term. And the same thing will happen for all the other terms in the expression as well. So as you start expanding some of these terms and you do the comparison, you will realize that because AB equals to BA, whenever you have A raised to N1, B raised to N2, A raised to N3, B raised to N4, whenever you have terms of this type, because of this commute property, you can actually write it as A raised to N1 plus N3, B raised to N2 plus N4. So whenever you have sequences of this type, you can convert them to sequences of this type purely because of the commutative property that's part of the assumption. And this identity will allow you to cancel terms on both sides of the expression and recognize that exponential of a plus b is equal to exponential of a times exponential of b, but the requirement is that ab should be equal to ba. Okay. So far what we have done is we understood, we have learned about this matrix exponential a few days back. I think in lecture 3, we talked about this matrix exponential. We used the Picard iteration to derive this matrix exponential expression. Today we are going to go deep into it. So what are the two properties we have learned so far? So if you have a diagonal matrix multiplied by t, you want to take the matrix exponential. It's exponential of the individual diagonal term multiplied by t along the diagonal. Okay, so off diagonal terms are equal to 0. So that's easy. That's straightforward. We did the calculation here and it's not quite difficult to see this expression. The second thing we learned is if AB equals to BA, then this identity holds. Now I want to move to more general A matrices. And in order to do this, I'm sure you have heard of this term called diagonalization of a matrix. Okay, so we are going to study diagonalization of the matrix for quite some time today. And what we will try to do is we will, okay, what we'll try to do is we will try to get a matrix in this particular form, then do the matrix exponential of this form and try and figure out what needs to be done in order to, well, we want to get to this form. We want to get all the matrices to this form, and then we can see what sort of behavior we'll be able to observe in this system. So let's think about it. Okay, let's recall all the stuff from diagonalization of matrices theory, and I'm going to do a recap of that theory right now. Any questions so far? So A Rn to Rn is a linear operator. This is same as saying that A is a matrix, n cross n matrix. If you want to impress other people, every time you see a matrix, you should say it's a linear operator. People will be impressed because not many people know what an operator means. So, definition, something we have talked about before. So, lambda is an eigenvalue and x is an eigenvector if and only if ax equals to lambda x. Generally speaking, lambda would be in complex domain, x would be in n-dimensional vector in the complex space, Cn. So this is n-dimensional complex space. How to find eigenvalues? This is called the characteristic polynomial of the matrix A. You take the determinant of A minus lambda I, set it equal to 0, and you find the roots of this equation. So this is a polynomial, this is a real polynomial. So the coefficients of the polynomial of lambda is, they are all real numbers because A is a real number. Okay, so we all know that roots of polynomials over real numbers could have complex values. So that's how we find the eigenvalues of the matrix. Spectrum of A is denoted by spec A. Sometimes some classes would use sigma of A, but I'm not using the term sigma because I need sigma as real value of a complex number. So I'm using spec A. Spectrum of A, which is the set of lambda I. One thing I'll note is that sometimes you have repeated eigenvalues. So spectrum, you will write those repeated eigenvalues as well. So example, spectrum of identity matrix 1, 1. This is n times. Any questions so far? I think this is all something that you have seen before. Spectrum of A, I believe, is a new concept for you. Spectrum is generally talked about in higher level mathematics classes. Generally low level mathematics classes, we don't really talk about spectrum. So spectrum of A is the set of eigenvalues of the matrix A, including their multiplicity. So identity matrix has n eigenvalues, all of them are equal to 1. So the spectrum will have n, we'll write the spectrum as 1 n number of times. So it's 1 1 1 1 1 1 1 n number of times. Algebraic multiplicity is the number of times ni, number of times lambda I appears in spectrum of A. So let's say I have a matrix 1 0 0 0 0 1 0 0 0 0 2 0 0 0 0 3. So what's the algebraic multiplicity of 1? So I see there are two eigenvalues. I mean, eigenvalue 1 appears twice in the spectrum. Therefore, the algebraic multiplicity is 2. But for eigenvalues 2, the algebraic multiplicity is 1. For eigenvalue 3, the algebraic multiplicity is 1. So here we have our distinct eigenvalues and summation of ni I equals 1 to r is equal to n, where n is the dimension of the matrix A. So matrix A is n cross n dimension. Okay. How many of you have heard of the term eigenspace? Eigenspace? One person? Okay. Two people? So it is Vi is the eigenspace, which is the kernel of A minus lambda I, and this is a subset of Cn. So this is the set of all vectors V such that A minus lambda IV equals to 0. So Vi is the eigenspace corresponding to the eigenvalue lambda I. Okay. Why is eigenspace important? Why should we care about eigenspace? So let's look at it. What's the important property of eigenspace? So if I multiply AV, or A times the eigenspace I is actually part of VI. So this is a fact. Is it obvious why this should be the case? So if I pick a vector V from this eigenspace, I multiply the matrix A to that V, I get a vector which is in that eigenspace itself. So Vi is A invariant. Let's look at an example. I mean, not an example, but let's look at an implication of this particular result on the linear system. So I have xt equals to, x dot t equals to axt, xt equals to exponential at x naught. Let's say x naught is in Vi. And let's assume everything is real, so we don't have to worry about all this complex business. What happens to xt? The question is, what happens to xt? So think about it. If x naught is Vi, then x dot of t is a times x naught. X naught is in Vi, so that must be within Vi itself. So the velocity, the x dot is going to be in the same space as Vi. X naught is in Vi. So you take one step. So take an infinitesimal delta t. You take a step in that direction. You are within that space Vi. Then you take another step. You are again in the space Vi, and so on and so forth. So let's see why how to get that expression rigorously. Are you all convinced that this is the case? Should I do a proof? I'll do a simple proof here. AV equals to lambda I V, and this is in Vi. That's because, so this is always the case because that's how we have defined the kernel. But why is lambda I V is in Vi? Because A minus lambda I times lambda I V equals to A times lambda I V minus lambda I square V. Okay. So all of us are convinced that this is indeed the case. Now let's look at the implication in this particular example. So I have this expression which is I plus at plus summation of a square t square over 2 factorial, not summation, times x naught I plus lambda I x naught t plus What is a square x naught? What is a square x naught? So remember x naught is in Vi. So I'll have lambda I square t square over 2 factorial x naught and so on. So this is the same as exponential lambda I t x naught. And this is a scalar. Remember that this one is a scalar. Okay. So eigenspace of a matrix A is important because if I start within that eigenspace, I will always remain within that eigenspace. I'll never go out of that eigenspace. Okay, this is the reason why if you inject the satellite in an orbit, it will always remain in that orbit. It won't go out of that orbit. That's not the case on Earth though. If I'm, the moon has been orbiting around the Earth for a very, 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 very long time. So it is in one of the eigenspaces of the dynamics around Earth. But why doesn't that happen on Earth? What's problematic on the surface of the planet? That moon is revolving around Earth, but we are not revolving on the Earth itself. What's stopping us from revolving around Earth? Sorry? No, not the reference system. Reference is what our origin is. That's not the reason.
Air resistance.
Air resistance and also ground resistance. Okay, so that's moving us along with the Earth because we have a lot of resistance on the planet. But if we are in this space, there is no resistance. There is no atmosphere. There is no resistance. You can keep being in that invariant subspace, which is the eigenspace. You can keep being in that eigenspace forever. Okay. So sun is revolving around Milky Way, Earth is revolving around sun, moon is revolving around Earth. There is Saturn ring, which is revolving around Saturn. All of those are in. So they all collected themselves in one eigenspace, and now they are always in that eigenspace. They are not going out of that eigenspace ever. So they are all A invariant. Okay. Let me write down another fact. Any questions so far on this? This is fact 1. If lambda I is not equal to lambda j, then Vi intersection Vj equals to 0. So I have two eigenvalues, lambda 1 and lambda 2 in a 2 cross 2 dimensional, for a 2 cross 2 dimensional matrix. I have two eigenspaces, corresponding eigenspaces. One would be something like this. So this is my V1. Other would be something like this, which is my V2. This is my V2. One thing you will notice is that the angle between V1 and V2 need not be 90 degrees. Okay, these are just eigenvectors, they need not be orthogonal. When are eigenvectors of a matrix orthogonal? Anyone remembers? Those of you who have taken 5500 should remember. You have not taken it. Nobody has taken 5500 yet. Okay. Well, when A is a positive definite matrix, if A is a symmetric matrix, then the eigenvectors are supposed to be orthogonal to each other. But in this case, it's a general A, it's not really a symmetric matrix. So the eigenvectors need not be orthogonal to each other. So eigenspaces they are just two planes or two lines that are intersecting only at the origin. And that's what this statement is saying, that if Vi intersection Vj, so the two kernels are only intersecting, two eigenspaces are only intersecting at the origin. If you have a 3D space, you will have one eigenspace that could be a plane like this, that could be V1, and then V2 could be something like this. V2 is just a line. And where are this line, V2 line, and V1, which is a plane, where are they intersecting? They are intersecting at the origin. So in this case, lambda 1 has multiplicity 2. That's why V1 is two-dimensional space. Not that's why, I mean, yeah. So if you have two eigenvectors that are corresponding to the same eigenvalue, then V1 basically is linear combination of the two eigenvectors. Okay. Third fact, which I'm pretty sure all of you know, if lambda in C, lambda is in the spectrum of A is in Rn cross n, then lambda bar, which is complex conjugate, is also in spectrum A. And I want to remind you what complex conjugate is. So lambda is sigma plus j omega. Lambda bar is sigma minus j omega. J equals to square root -1. Any questions so far? Okay, perfect. So if you have a real valued real matrix, you have a complex eigenvector, then the conjugate of that eigenvalue, then the conjugate of that eigenvalue is also an eigenvalue of the matrix A. Perfect. Today, I want to spend quite a bit of time talking about the case when the summation of dimension of Vi I equals 1 to R is equal to n. So you take the dimension of the kernel of A minus lambda I, you sum it up, you have n dimensional space. So this means okay. The notation, this notation, I don't think I have introduced it, but this notation essentially means you have V plus W equals to V plus W such that V is in V, W is in W. This is the set sum notation. So when you add two sets, you take the individual elements of the set, you add them up, and that gives you the set of two the sum of two sets. Yes.
So is n number of distinct eigenvalues?
No, n is the dimension of A in the sense that A is Rn cross n dimension. So throughout n is fixed, n is the number of rows in A, and A is a square matrix, so it's also equal to the number of columns. Okay. So I think the question comes from the following situation. So I know that some of you have heard of this term diagonalizability of the matrix A. So one of the things that happens with A, if A has distinct eigenvalues, if all eigenvalues are not equal to each other, then you have n distinct eigenvectors. If you have eigenvalues with multiplicity, you could have distinct eigenvectors, you may not have distinct eigenvectors. So we are looking at the situation where you have multiplicity of eigenvalues, but you have distinct eigenvectors, as a result of which the dimension of Vi is equal to Ni, and you sum the Ni's and you get equal to n, because you always have n eigenvalues. Okay, so we have matrix A, we have n eigenvalues, and we have Ni distinct eigenvectors corresponding to eigenvalue lambda I. Lambda I with algebraic multiplicity Ni. So lambda I has algebraic multiplicity Ni, and you can identify Ni distinct eigenvectors for that particular lambda I, then your dimension, then the dimension of Vi equals to Ni, and summation of Ni is equal to 1. So that's the flow of argument here. I want to ensure that you understand this idea very well, that you could have the same eigenvalue multiple times. So you could have a lambda I with algebraic multiplicity Ni, but they need not have Ni distinct eigenvectors. And then we'll talk about Jordan canonical form. That's the topic for the next class. But in this class, I'm assuming that if lambda I has algebraic multiplicity Ni, then I have Ni distinct eigenvectors that I can compute. And if you go to MATLAB and you compute it, you will be able to figure it out, that you can get Ni distinct eigenvectors for that. And in that case, I am in this particular situation, where my entire complex space is spanned by the individual eigenspaces, sum of individual eigenspaces of that matrix. Okay. So let's look at the following case. So all of the discussion is from module 2.1 from Professor Andrea Serrani's notes. So you have all the presentation on the Carmen, so you should be able to get access to it. So all of this material is taken from there. Okay, so I have n eigenvectors, n distinct eigenvectors, and let's call them v1, vn. And let me call the matrix T. I'm going to stack all these eigenvectors and I get a matrix T. What is AT? That's A times V1, V2, Vn, which is the same as okay. This seems familiar. So V1 is an eigenvector. So what is AV1? This is lambda 1 V1. This is lambda 2 V2, lambda n Vn. And this can be written as V1, V2, Vn, lambda 1, lambda 2, lambda n, 0, 0. And this is T itself. So I have AT equals to T lambda. This matrix is denoted by lambda. And this implies that lambda is equal to T inverse AT. Lambda is a diagonal matrix. So this is called, and when you do T inverse AT, that's a similarity transformation. So we did a similarity transformation of the matrix A. We got a diagonal matrix, and this process is called diagonalization process. So let's go through the chain of thought. The chain of thought here is I have multiple, I have eigenvalues with certain multiplicity. Turns out that I still have distinct eigenvectors, as a result of which the dimension of the eigenspaces, the sum of dimensions of the eigenspaces is equal to n. So in that case, what I can do is I have n distinct eigenvectors. They are all linearly independent. They have to be linearly independent. In which case, I can stack them as a matrix in this particular fashion. Turns out that if you do AT, what you get is T lambda. Now I can take the T on the other side because T is an invertible. T is invertible because all of these are linearly independent. So T is invertible, so I can take the T to the other side. I get a diagonal matrix equals to similarity transform of the matrix A. You can only do this if you have n distinct eigenvectors. So you can do this for identity matrix. even though you have the same eigenvalue n times, you have 1 1 1 1 1, that those are the eigenvalues, but you can construct n distinct eigenvectors for the identity matrix, which is 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0, and so on and so forth. Those are all n distinct eigenvectors corresponding to the eigenvalue 1. So I can construct this matrix T that allows me to diagonalize the matrix A. So this process is known as diagonalization of the matrix A. Yes,
Is there a
please.
way to know if you have n distinct eigenvectors without going through and actually just calculating out all eigenvectors?
There is no other way to know. You will have to do the individual calculation of eigenvectors. Of course, I think certainly all the SciPy package in Python, or sorry, NumPy package in Python, or MATLAB has codes to compute the eigenvectors. So they will definitely be able to tell you. But more importantly, computing the eigenvectors, I think it is complex. It has a complexity of n raised to 3.5. That's roughly what the computational complexity is. I could be mistaken. The exponent could be different, but I think it is 3.5. I haven't checked recently, so anyways, it's going to take, if you have a very large matrix, this might take a long time. But if you have a small matrix, it's not that difficult. Yes.
So just quick question. So what was the right side again called? You said similarity transformation of it?
Yeah, this is similarity transformation of A. So you multiply it by a matrix and you pre-multiply it by the same matrix inverse. That's similarity transformation. We talked about it in the change of basis in lecture 2 or lecture 1. So I'm just recalling that same stuff here. This is equivalent to changing the basis from the original basis, the typical basis in the Euclidean space, to V1, V2, V3, and so on. That's the new basis. And this is the similarity transform that changes the basis, and the updated dynamical system looks something like this. Okay. So we did all this mumbo jumbo. What's the whole point of doing this complicated analysis and doing this diagonalization? Remember, what we are interested in is exponential of AT. Excuse me. What's the expression for exponential of AT? So let's get to that. I don't care about the linear algebra. What I care about in this class is what is exponential of AT. Complicated. So I have a general matrix A, but I'm under the assumption that I have n distinct eigenvectors, so I can write T in this particular fashion. This is I plus A AT plus A square T square over 2 factorial, so on. Here is what I'm going to do. I'm going to pre-multiply and post-multiply by T. Can I do that? I'm free to do that. T is invertible. I have a matrix. I can pre-multiply and post-multiply by whatever matrix I want. Okay, this is a free country. I can do whatever I want. Do we have a pattern here? I have identity. T inverse AT is lambda. What about T inverse A square T? What is that? Here is what I'm going to do.
square t?
Yeah, so I multiplied by t inverse in the middle. So I have a square. I multiplied this t inverse in the middle. This is identity matrix, so I get a square. So it's the same as this. But guess what? Now I have t inverse at multiplied by t inverse at. So what I have is identity plus lambda t. I think I'm missing this t everywhere. Okay. What is exponential of lambda t? So I have exponential of at, sorry, t inverse at equals to exponential of lambda t e raised to lambda 1t e raised to lambda nt. So this implies that exponential of at equals to t times exponential of lambda t inverse. So when I have n distinct eigenvectors, they are all linearly independent. I can construct this matrix T and I can diagonalize the matrix A and I can compute the matrix exponential, which seemed like a hopeless thing to do. For every time t, I have to compute this infinite sum. That's hopeless. Nobody wants to do that. So what I have done is I have transformed a hopeless expression which into an expression where what's the computational complexity of t, computing t? Well, you have to compute all the eigenvectors of the matrix A. That has some complexity, but typically if A is of the order of 1000, you can run it on your MacBook Air or your computer with 16 GB of RAM. You have a 1000 cross 1000 matrix, you can compute this matrix T. This is a brainless operation, at least for graduate students at OSU. You don't need to spend a lot of effort into computing this matrix. And this one is again easy. Once you compute T, you can compute T inverse as well, and you can store it in your memory. So that way you don't have to compute T inverse at every point of time you want to do the simulation. So you have T in your memory, you have T inverse in your memory. You can compute this very quickly, and now you have exponential of at, and then the solution to this is exponential of a t minus t naught x naught. So this computation has become easy. This computation, I mean, now you have to multiply the matrix by a vector. That operation is very simple and straightforward, and that helps you solve the problem. Okay. Now this all works beautifully if all the eigenvalues were real numbers. So if lambda 1 all the way to lambda n are real numbers and all this is real valued eigenvectors, then this whole thing works beautifully. Okay, then we don't even have to worry about complex numbers and all that complex conjugate business. Well, let's assume for the time being that one of the lambda is complex number. Okay, and the problem that happens in that situation is if lambda is complex, most likely your eigenvectors are also going to be complex. Not always, but eigenvectors would likely be complex. And I know we don't have time, so I guess I'll cover this topic in the next class. But I'll give you a preview of what we are going to do. So I want to look at the case lambda is complex, and then I'm going to look at the case summation I equals 1 to r dimension vi is less than n. And in this case, I'm going to talk about Jordan canonical form. So matrices that have this sort of property, they are not diagonalizable. You cannot diagonalize it. So all of the stuff we talked about today doesn't apply. Well, some part of it applies, some part of it doesn't apply. So we'll figure out how to compute this thing. How do we compute this and with the Jordan canonical form, so which is not diagonalizable or non-diagonalizable matrices. So the first thing we'll do is talk about when eigenvalues are complex numbers and then corresponding eigenvectors. So where lambda will be sigma plus minus j omega, and the eigenvectors v would be u plus j w plus minus. So this is your eigenvalue, this is your eigenvector. Can we simplify this process for this particular situation? And what I'm going to do in this case is I'm going to construct the matrix T in a somewhat different fashion. So we'll use U and W in the matrix T, and then we'll figure out how to massage this expression so that we get a simple expression right here. Okay. So what we'll see actually is you will have cos omega t, sin omega t, minus sin omega t, cos omega t here. Okay. So that'll be like, you will get like dreams from signals and systems in the class when we talk about that stuff. And then Jordan canonical form, I'm pretty sure many of you have not seen it before, or you might have seen it very briefly. So we'll go into depth of Jordan canonical form and we'll talk about that. So thank you so much, and see you next Tuesday. Oops, I'm so sorry.